Hi student and audience, this is lecture number 6. So we went through all the details, theoretical details about the column mode control, and we are ready to design the practical column mode controlled buck converter. I'll take the buck converter example, but that this procedure can be extended without any modification to the boost and buck boost converter. After this lecture, I'll present the design of column mode control for the boost converter. And in the next topic, I'll provide the full details, okay? Virtually, really full details about the flyback, column mode controlled flyback converter, employing optocoupler isolate column mode control. It's called offline flyback converter for the consumer electronics. Okay, that is the real application in industries. So that is the next topic. Maybe topic, this is 10 or topic 11 will be that one. This is topic 10. Okay. Okay. Here maybe we repeat some part. Okay, we already went through this, but somehow I think it's not a bad idea to repeat the design procedure. So first, I'll discuss the power stage parameters of this design example and the column loop design. I'll provide you some numerical values, and the voltage loop design, I'll provide the component values for the every feedback circuit component. And finally, this is very important, I'll compare the performance of voltage mode control and the column mode control and the difference between them. How the column mode control differs from the voltage mode control, and what is the real advantage of column mode control when we lose the benefit of the column mode control, in what manner, what fashion, if you misunderstand something. Okay, so so this is the design example for converter. We are using this converter from the beginning of this lecture series. Okay, so same value. Okay, and this is column mode control. Column mode control is employed, and from this we determine this, and this omega ID is the 0 in the control to inductor current transfer function. And the KID is DC gain of that transfer function in duty ratio to inductor current transfer function. Okay, and because we don't have any resistor, our value is regulated at 4 volt. So duty ratio is this one, and the switching frequency is 50 kilohertz. Okay, this is the radian per sec, and the maximum value of allowable voltage at the input port of this PWM chip is assumed 5 volt, so Vmax is 5 volt, and this is the IL peak calculation with duty ratio of 0.5, this 1/4, okay, so this is the duty ratio D, and this value is 4.75 M, okay. So this is a procedure of column loop design. Okay, only one step, selecting this number between 0.1 to 0.3 or 0.1 to 0.5. Okay, so difference between 0.1, 0.2, 0.3, 0.4, 0.5 will be explained later. Okay, this is a good number, but this is a little conservative selection. Maybe you can go up until 0.5, but somehow I selected this one. I assumed I selected this one. Then this omega CI is determined. Okay, you selected this. You selected one number. Then this is the DC gain of current loop, not current loop gain, is KI is given by this. So you evaluate this. So this is coming down. So with this number, you evaluate this, and this KI will be used later here. So KI will be used here, okay? So they are combined. This is something else. And the CS again, Ri, is determined by dividing this maximum allowable voltage at the PWM input, Vmax divided by, this is the peak value of inductor current, not sensed, inductor current. So this number is this one. So Ri should be this. So I selected Ri, this one. Okay. You know how this Ri is determined? Ri is, if you recall the previous lecture, is 1 divided by N. N is turns ratio of current sensing transformer times R sense. Okay. So somehow, based on this number, you determine these two numbers. Okay. There are infinity different selections, but you select the reasonable one. Okay. And you evaluate the FM, required FM prime. Okay. This equation is derived from the graphical analysis, and this equation is given by definition of Ki. Okay. Then you determine this, and this Ri is coming here. So Ri is coming here. Then Fm prime is determined. Then Fm prime is coming here. Okay. So Fm prime is determining this one. Okay. This is just the rearranged expression of modulator gain of current mode control. Okay. Then finally you calculate this, and this is the minimum value of the SE to avoid the subharmonic oscillation. Okay. This plus something is larger than this, which is this one. So this is stable. Current loop alone is stable. Okay. So this is the design result. This is the design result. You only have two design results, this one and this one. And this is the maximum value of the VM. I used this number for the PSIM simulation. Okay. So this is the current loop design. It's very simple. Okay. And we discussed the best structure of this voltage feedback compensation is this two-pole 1-0 structure. Okay. With that, we obtain this kind of loop gain. Right. So this compensation 0 is coming here. This is coming here. This is omega GC, and the power state double pole frequency is somewhere in the middle. After this, below this, loop gain crossover frequency, 0 dB crossover frequency of this loop gain. Okay, this is a loop gain, not a loop. This is a loop gain, and expression of this is, we went through this, so we know this. This is TV divided by 1 plus TI. Okay, later on we will be using this. Right? So we didn't discuss this before. Okay, we directly write that down, but this is the real definition or another definition. Okay, so this is a structure. So this is very good. Why is it good? Because this the slope of this loop gain at this 0 dB crossover frequency is about -1. So you have that phase margin will be very large. Okay, something approaching to -90 degree, but less than -90 degree, and the structure very similar to the ideal structure of this simple integrator. The -1 slope from the beginning to end is very similar. Okay, so this is the desired one, and we find out the structure of this using the graphical analysis. This and this structure. Okay, all right. So nothing is new here, and these two things are cancelled. Intentionally, we cancelled. Okay, to make this part. No, not this part. This part straight. This part straight. To have -1 slope for the wider frequency range, we cancelled this. Okay, so omega PC is located at omega ESR to cancel the effect of the omega ESR, and omega GC is coming before omega naught to boost the phase of loop gain at here, and it comes before this to to avoid being conditionally stable. And KB is determined, this gain is this one is determined to locate omega CR at the desired frequency, and omega CR can be placed at omega ESR or slightly lower than that. So the suggested number is this one, 30 to 100% of omega ESR. If ESR is large, then you can move this direction. ESR is small, you need to move this direction. Okay? This is more aggressive design. This going this direction is conservative design, safe design. Okay? All right. Okay? So we know almost everything. Okay? But we determined this, then we need to calculate this based on the frequency selected here. Okay? So for that purpose, we are using this. Okay? The loop gain magnitude at this frequency is this. Initially, this is an integrator, S is here, and the integrator gain is this one, this times this. So initially, this line segment is looking at this point, so it goes this point, right? Then you evaluate that this line segment at this frequency, that value is this one, okay? So this value is A, okay? Note this as A, this is A, right? So it starts from A, and it decreasing with -2 slope from here to there, and this frequency was omega ID. So we have this term, all right? So we have this is integrated gain. It was S, and you replaced S with this omega ID, is this value, and that value is declining with -2 slope from here to there, and this declining slope is -1, shown here. This is 0 dB at omega CR. This is the log equation. You change this to linear equation, then this is the design equation. Suppose omega CR is determined somehow, then that value KB, this KB is providing omega CR as the loop gain crossover frequency. Okay? So you don't need to calculate anything other than this. It's called algebra on graphics. Okay? All right. Then again, this is summary of the previous selection. This is the TMS expression shown here. Okay. So this part is GVCI. This is the voltage feedback compensation. Omega PC. You select that lower value of omega ESR or have the switching frequency. Okay. Usually this is much lower than this, but somehow you select very good capacitor with extremely small ESR, then this value come later, then you select this one. Okay. So select the minimum of either this one or this one, and omega GC is selected here. Okay. If you go to this is very little bit dangerous. If it exceeds this, system becomes conditionally stable. But this determines the speed of every transient response. Okay. Later on, you will see this, right? So if you move this direction, you are safe, but transient response will be slower. So as a trade-off, maybe this is a good number, somewhere maybe 0.7. Okay. And loop gain, crossover frequency. This is the case for the buck converter. Boost or buck boost converter, everything remains same, but this will be changed. Okay? Because of the presence of the RHP0. Okay? There is RHP0, then this will be slightly modified. Okay? This number is modified, and this omega is modified. Okay? It will be changed to omega RHP. That comes later when we discuss the boost converter and evaluate DC gain KV, okay, based on the previous equation, and check the phase margin. And if phase margin is not acceptable, you are not happy with the phase margin, then adjust this one a little bit. But you don't have, probably you don't have any iteration. Okay, you will get the almost optimal design at your first trial. Okay, and evaluate the feedback compensation, circuit parameters of voltage feedback compensation based on, we had one equation here, right? This equation, okay? So there are 4 variables to select, and you have only 3 equations. Then select one arbitrarily, maybe 10K is a good number. Then based on this equation, remaining 3 parameters will be determined almost automatically, okay? Okay, this is the procedure, okay. Let me go through this. Okay, this is the procedure, and this is the design output. Okay, so compensation pole is selected at omega ESR because this frequency is relatively small. That means ESR is large, relatively large. So you select this, and compensation 0 is selected this. Maybe some aggressive design. Okay. You can go down 0.7 something like that, but this is okay. This is okay. And the loop gain crossover frequency, we select this, okay, because this is large. This is large, okay, and you select this. Okay. It was 0.321. Okay, I selected 1 and calculate this, and these values are from the power stage parameters, and everything is determined. Then KV. Everything is determined. KV is determined, and this corner frequency are all determined. Omega PC, omega GC, KV is determined, and this is given. Select R1. The arbitrarily select R1 as your 10K ohm, and this will provide this and this. Okay, so this is the final design of your converter, which is this. This is the schematic diagram of buck converter with complete current mode control. As I addressed several times or many times, the only truly meaningful design step is determination of the slope of this compensation lamp. So we selected these as the compensational lamp slope. Then we evaluate the closed loop performance of a converter to confirm the validity of our control design process. So this is the loop gain characteristic, and this lecture slide little bit busy, okay, but it has a lot of information about the implication of loop gain characteristic of this current mode controlled converter. So this is the simulation result. This is the PSIM model to simulate the loop gain of the converter with current mode control, and this is the result of the simulation. So it looks complicated, so I'll explain one by one. First, there is a connection inside of this model. So this switch current is sensed with this current sensing network gain and fed to this input port of the PWM modulator, and this is our voltage compensation. Okay. And this is the something you need to use to measure the loop gain of this converter, or to simulate you need this, and to measure experimentally you need something very similar to this. Okay, and this shows the loop gain equation of with current mode control. So loop gain is this one. GVCIS is control to output transfer function with internal current loop closed times this FB is this transfer function of this voltage feedback circuit is a loop gain. Okay, but expression of this GVCI is this is the GVD times FM prime divided by 1 plus TI. This is the expression of the GVCI derived using the Mace's gain rule from the previous small signal model with current loop closed. Then you combine the 1 plus TI. TI is current loop, not current loop gain. And you combine this all together, three terms, then this is the voltage loop. T, this is the duty ratio to output transfer function, and this FV and the modulator gain without current loop closed. Current loop is open, then this will be TV. Okay. So final expression of TMS is originally it was this one, and it can be modified or rearranged in this form. Here TV divided by 1 plus Ti. Ti is this quantity, current loop, transfer function of the current loop, not current loop gain. Current loop gain is something different. Okay. So here, for the current mode control, TMS loop gain is TB divided by this one. This one is usually larger than, much larger than unity. Okay. Okay. This is something else. Think about the current mode control. Then we don't have this part. We are missing this part. Then there is one loop, which is this loop, voltage loop. Now, then there is duty ratio to output transfer function times this voltage feedback compensation times modulator gain. That is the TB. This is the voltage loop. And the loop gain, they are same because there is no internal current loop in here. Okay. So, to avoid some confusion, I denote it as TMS, and the TMS prime is the loop gain in the voltage mode with voltage mode control. That is just the TB. This one is TB divided by 1 plus Ti. This TB, they are same thing. Okay. Then obviously this TM prime S is much larger than TMS because you are dividing something which is larger than unity. Okay. So this means the current loop is better than voltage loop. No. Voltage mode control is better than current mode control. I said that is not true. Absolutely not true. Okay. We are looking some two different things. So you cannot use one single measure for two different loop gain definitions. Okay. Okay. There is one. And this is the simulation result of this classical model. So classical model with shown this black line. Okay. And this is the phase of classical model. All right. So this classical model totally ignores the sampling effect of the current mode control. We will study in detail the sampling effect of the current mode control later. So now I'm giving you some prior information about that. Okay. And this, so this is the classical model prediction, which does not consider the sampling effect at all. And this is the new prediction with sampling effect included. Okay. You don't have a model here, but later on we will have a model. If you use that model for this simulation, then probably you will have these three different cases. So at the half switching frequency is 50 kilohertz. So at the half of that value, 25 kilohertz, there is a peaking. A, B, C, different peaking. Okay, depends on the selection of something, the peaking will be different. Okay, and at this switching frequency, there is this dip to the negative infinity. This is the prediction of Middlebrooks PWM modulator model, and this is the needless prediction of sampling effect of the current mode control. Okay, if we take a look at this, below this frequency, this is a classical model and the new model, including sampling effect proposed by Needley. They are exactly same up to this point. Okay, and after this point, this is the prediction of classical model, which does not consider the sampling effect, and this is the new model proposed by Needley. Then you have the additional phase delay, and this additional phase delay is the same as the prediction of Middlebrooks modulator model. Okay, somehow this the sampling effect is a combination of this new finding of Needley and the old knowledge of Middlebrook. Okay, somehow they are mixed up. So people got confused. I got confused. I don't know why it happens. Okay. Later on, we'll go through all the details about derivation of this. And suppose you have this A, okay, case A has small peaking, and the case B has larger peaking. The peak value is just touching this 0 dB line, and you have case C, which exceed this 0 dB line. Okay. Suppose this is the polar plot trajectory of loop gain. Okay. For the case A, for the classical model, suppose it goes here and it goes directly to the origin without any eccentric behavior, strange behavior. Okay. But if you include the sampling effect, it goes like this because there is this one. Then this magnitude is larger, is getting larger, and it circle around and go back here. This is a unit circle, and this is a critical point, minus and 0. So this purple curve remains within the unit circle. Then there is no impact on the stability. If you remind the diffuse stability, you are trying to reach from here to there to the origin. So it goes without touching this. That means the system is stable. Okay. But if you goes like this, then you should cut this. System is unstable. But it go around, and come back, and it goes like this. Then you should cut here. That is unstable. Okay. All right. So this one is there is a peaking, but still stable. A is stable case. B is this pink one. It goes here and go around here, and just touches this critical point and go back to the origin. That means it is increasing just up to this 0 dB point and comes down. Okay. What is this? It is marginally stable. That it will generate sustained oscillation. And for the case C, it goes above this 0 dB line. That means this one goes to the out of a unit circle and coming back to origin. Okay, so during this part, it travels outside of the unit circle. Then it must cut this to get this origin. The case C is unstable case. Okay, so I wrote down here, A is a stable case, B is marginally stable case, C is unstable case. Okay, suppose this, you have this, some special case. So this peak is very large, like this. Okay, but you cannot judge stability by just looking this peaking. Okay, somehow the phase characteristic is a little bit different from this. So that case, if you go here and go around here and go and circle this part, then system is still what? Stable. Okay. To be unstable, this polar plot trajectory should encircle this, making this large circle around here. It does not affect the stability at all. Okay. This kind of analysis is very important when you are analyzing the interaction between two subsystems. You have one stable system, another stable system. You connected them together, then combined system can be stable or unstable. So this kind of analysis is very useful tool to predict, stabilize, and or to improve design, to have larger stability margin. Okay. All right. How about this peaking? Magnitude of the peaking is Ridley. He proposed some equation of this QP. Okay, there is an expression QP, and the peaking is given by this 20 log QP is peaking. Okay, if larger the QP, peaking becomes larger, and the QP is very large. It goes above this 0 dB line, and for this case, it usually makes the converter unstable. Okay, because of this phase characteristics. So this is the prediction of classical model, but in this new model or Middlebrooks model, there is additional phase delay and 90 degree at the half switching frequency and 180 degree at switching frequency. Okay, because of this encirclement of this kind of encirclement usually occurs. Okay, so to avoid this, you should minimize this. Okay? So he proposed something like this. QP is some complicated expression, and he recommended you keep QP some value in between. Maybe 2 might be dangerous, but still acceptable. 3 can be okay, as long as it does not touch this. But if the operational condition changes, the peaking will grow further, making the converter unstable. So this is the safe design guideline. Okay, that is his story. That is the result of this new model. This new model, it was new in the about 20 years ago, but it's not new anymore. But still, it is called new model because he named it as a new model. It's not new, but we call it new model. Okay. And this is my new fact, new finding. I found this about 10 years ago. There is a relationship between this. We will prove this. Okay, this is the number which determines the magnitude of the peaking in this new model. So this QP divided by 2 is the same as omega Ci is current crossover frequency, and this is the switching frequency. Okay, so in the classical model, they determine the ratio between this. The suggestion, the recommendation in classical model by the Dr. Fred C.D. was this one, okay, 0.1 to 0.5 of this is the switching frequency. So this is his recommendation and my recommendation, and this is my finding. So there is this relationship is exact relationship, all right? So if you select this one, okay, I said you can go as large as this, okay, then this is the 0.5, then you put 0.5 here, then QP becomes 1. With QP 1, there's no damping, no peaking, okay? 20 log QP is 0 dB if QP is 1, so there's no peaking, okay? Maybe there is something, but there's no peaking, all right? So if you use this rule, then you are safe. Okay, you don't have any problem. Okay, using this new model, you design the feedback compensation according his rule and select this value QP2. Then that is the same as omega Ci is omega S. Okay, so there is a 1-to-1 correspond between these two guidelines. Okay. So this new finding is actually unnecessary. It is necessary to understand the behavior of this, but as long as the design is concerned, if you are properly design the converter, this extra lamp slope, then it won't happen here. Okay? If you select the bad design somehow, then you are seeing this, but there is no chance to this peaking becomes this large as long as you keep this rule. Okay? Then what is the difference the classical model and the new model? With the new model, you can see this. Okay? You can see this. The classical model, it does not show this at all. Okay? It's showing same thing. Okay? Over and over. All right? But you don't have to see this if you design properly. Okay? So I said this new model is pushing you to see what you don't have to see. That can be true, not totally, but partially it can be true. Right? You understand this? Okay? So this is very important. Right? So this is same thing. Okay? So if you understand this, it really helps to understand the sampling effect of the current mode control. Will be discussed later. Okay, so this is about loop gain, and let me write down this. This is the classical model prediction. Classical model prediction, and this And this is effect of outcome of sampling effect of current mode control, CMC. All right. So actually, this is new from his model. Only this one. Okay. You get that point later. This is about loop gain. And this is about the output impedance. Okay. So this is the setup for the output impedance measurement. You can go to this lecture if you have interest in this. Okay. It has the complete detail about this measurement setup. So this can be used for the simulation and also can be used for the hardware measurement. Same is true. This can be used for the simulation and for the hardware measurement, something similar to that. Okay. Let me show the output first. This is the plot. This is the plot, the PC model, and this is the simulation result. This black line. So this is a black line, and I draw some line here. So this is the one line segment, and another line segment, and this is the pole frequency. This pole frequency, of course, omega GC. Later on, we prove this. Okay, this is the compensation 0. All right. By changing this, you can change the this corner frequency, and the high frequency value is always 20 log C or something very similar to that. Okay, let me explain this. This is the expression for the output impedance. This for the voltage mode control, it was open loop load current to output transfer function, which is denoted as GP. Now it's different. It's GOI. When you are thinking about GP, this current loop, where is current loop? This current loop was not existing. Without current loop, it becomes GP, but with this current loop closed, it's something different because there is an internal loop here. This VI is connected here. So there is an internal loop. If there is an internal loop, you have to divide by 1 plus Ti somewhere. So this is different. This is the open loop load current to output. Load current to output transfer function with current loop closed. It's different from the case of the voltage mode control. So I use notation of GOI. I means current loop closed. Okay. So this is, we'll analyze this later. Okay. This is rather complicated, but if you use the asymptotic analysis, that can be easily solved. Okay. But at high frequencies, this TM becomes very small, can be ignored, and this current loop becomes very small, can be ignored. Okay. Then this is the same as open loop output impedance. Okay. This is true for the voltage mode control and the current mode control, because if this frequency increase, this TM becomes very small, and the internal, this loop, because there is a Dewey ratio to inductor current transfer function has this kind of feature, so it becomes very small. So this is true. Okay. So at high frequencies, regardless of your control scheme, this circuit looks like this. Okay. I explained this many times. Input side is all shaded, then SL, RC, CR. This is the configuration of output impedance at high frequencies for the voltage mode control and the current mode control as well. Then this is the GOI. Okay, GOI is different from the GP. GP was something like this. If you think about the buck converter, voltage mode control, GP was something like this. Okay. Now GOI is something this one. Later on, you prove this. You predict the corner frequency here and here. Okay. Through the asymptotic analysis, and the outer loop gain. Outer loop gain is something similar to this. Okay. This is the TM. So this is the open loop here. This in this case, open loop means this voltage loop is open, but current loop is closed. For that case, the open loop with the current loop closed, output impedance this one, and this one is attenuated by this much. Suppose this is 0 dB, then this will be attenuated because of this 1 plus Tn. Then this is the final output impedance. Okay, so this is the way of understanding this. Okay, just seeing this does not provide any good information. But if you understand this, you understand the mechanism behind this, and you know how to improve this, where everything comes from. Okay, all right. And the final value of this. Okay, so transfer function of this is very obvious. You have this is the what? This is the integration. So you have this line segment at the frequency of omega m. It becomes UDB. So this is the 0 dB line here. Suppose you know this frequency, then you have this integration, and you have one pole at omega gc. So this is the transfer function. Okay. Then high frequency value of this value, maximum value. Suppose this is very small. So high frequency value is the maximum. Then when evaluating the maximum value, you ignore this and you put omega gc here. Then this is the maximum value, and that should be same as RC, because from the circuit diagram, high frequency asymptote is RC. So the result is this one. Okay. Okay. This is about output impedance, and output impedance is closely related with step load response. So we did this. We did simple calculation. This is not a circuit analysis, anything. This is an extremely simple example. Too simple. Okay. They don't treat in the undergraduate course. This is so simple. Okay. All right. This is the circuit diagram or PC model for the step load response. I have two switches. When this is on, this off. This R is the load resistor. Otherwise, this one is load resistor. So by alternating this, I can introduce this step load response. Okay. This is the result of the step load response of our voltage. So our voltage regulates at 4 volt. It has ripple and it goes like this. From this analysis, we can predict this value, and we can predict this settling time, and we can closely predict the behavior of this. Okay. So this is the step. This is the S domain expression of step. Then we multiply the S domain expression of step load change to output impedance. That becomes S domain expression of our voltage, and you take inverse Laplace transformation of that. This is very simple to figure out. Okay, then it becomes like this. This is the exponential function, and we know this is RC from the previous analysis. So this is RC. Then it becomes I step times RC times this exponential function, first order function. Okay, the maximum value of this occurs at time equals 0. Then this becomes 1, and this is the maximum value. So maximum value is this, and this is 4. I think I didn't show this, but this is a 4M, and the ESR is 0.1. So this step is 0.4. Okay. And this is what? This is the time constant. Okay. This is the pole frequency. 1 over this is time constant. So time constant of this response is this one. And this is 5% settling time is 3 times time constant. Okay. 5% means this output value, average value of this remains 5% of the final value, and it remains within 5% bound. Then this is the number, and this is 0.5 millisecond. Okay, this is the prediction based on this simple analysis, and this is a simulation result. Okay, so if this is the entirely purely linear system, it starts from 0. But this is a converter, So we have this value, 4 volt was initial value. So, okay, look at this, okay, initial value. So it jumps up. This is initial jump. This is instantaneous jump. This ESR, okay. Then value of this is 4 times this step. Step is I step times RC, which is 4.4 volt. Okay. Just take a look at this envelope or average value of these waveforms. This is very exact. Okay. So this is very special because this simple linear analysis, the analysis for the knowledge on the linear time invariant system provide almost exact information about this nonlinear PWM converter because we have small signal model and because we have the tools, asymptotic analysis and so on, and design tool, everything is there. Okay, so with this you can predict the accurate behavior of this one. Okay, this is some digress. Okay, think about this. So this initial value of jump. Okay, that's called the initial jump. You know the initial value theorem is coming from the Laplace transformation. You have the table of the formula. Then this initial value is this is S domain expression of output voltage, not output impedance. This one, entire one, and you multiply S in front and send S to infinity. That is this value. Okay, T goes to 0. That is the initial value. Then you put number here, expression here. Then they cancel because S goes to infinity. You take just coefficient of this. Then you have this same as this analysis. Okay, so maybe you can use initial value theorem or you can use this. Okay, initial value theorem and the final value theorem is very convenient to evaluate the asymptotic behavior of time domain response using S domain expression of some transfer function. Okay, so maybe during this period of time something happens. But you are only interested in this, then you use this initial value theorem. Okay? All right. This is about it. Audio susceptibility has the similar behavior. Okay? This is the audio susceptibility is 1 plus Tm comes in the denominator. This is what? This is the input to output transfer function with current loop closed. So this is different from the case of voltage mode control because there are current loop here. So the presence of the current loop, the situation becomes a little bit complicated. So this is with current loop closed. Right, and we analyze this. Then this is the expression. Okay. Then from this graphical analysis, you predict the. I'm not talking about this is reduced to this, not that. Okay. This is one expression. This is some mathematical expression, and this is the expression derived from this simulation result using some asymptotic analysis. Maybe this can be approximation like this. Okay, so this is the closed loop input to output transfer function. So this low frequency line segment and some mid-band gain and the high frequency asymptote. Okay, so the big difference is compared to this with output impedance. Output impedance has this finite value, but this input to output transfer function audio susceptibility has -1. Declining slope at high frequency. Okay, why is that? This is at high frequencies, current loop becomes very small, and this Tm becomes very small. That becomes what? Input to output transfer function of open loop power stage. What is that? That is low pass filter. It was low pass filter, so this low pass filter characteristic should come out at high frequency. If you have this kind of characteristic, that is absolutely wrong. Okay? at high frequencies, everything reduces to the open loop transfer function. Current loop disappears. Okay, so this should be, this has -1 slope, and that changes the equation of this one little bit. Okay. For the output impedance, you have only these two terms, but you have another term here because of this and because of this low pass filter characteristic of this output impedance at high frequencies. And the first corner frequency is determined by compensation 0, and this second corner frequency is determined by Tm crossover frequency. We denote it as omega CR, and during the design procedure, we placed omega CR at omega ESR. Okay, so this is they are same by design, and this is a characteristic of this. And this one is open loop. This one, open loop input to output transfer function with current loop closed. Okay, this one. Or original one was everything is open, so you have a power stage alone. Then maybe this one will be something similar to this. Okay, it was low pass filter. Okay, but with this current loop, this much is reduced. So you have this, and with this Tm, you have further attenuation of this much. Okay, so maybe loop gain. If you overflow loop gain, there will be something. It's not exact, but you can imagine this, something similar to this. All right? Okay. So if you have this plot, you know everything about this, then you take the inverse Laplace transformation, same as the previous case of output impedance and step load case. You do same thing here, okay? But this is the S-domain expression of V-step, and this is the audio susceptibility. They cancel, and you have this one. Then you have these two exponential terms. If you want, you can calculate this, but that is very trivial. That is meaningless. Okay? Children's play. This is not engineering, but if you want, you can do that. Okay? But that is unnecessary. But you can find out one is positive, one is negative. Okay? And they are different. This omega GC is somewhere here, and omega CR is here. So time constant is different. So this one is very slow, and this one is very fast. The slow term is here. This is slowly decaying first order term, and this the fast decaying exponential term with negative sign. Then, and you can prove this. This length should be the same. That can be inferred from the final value theorem. Okay, from the initial value theorem, you determine the initial step jump with the final value theorem or initial value. I think initial value theorem. You can prove this should start from the 0 without any jump. Okay, then means the length of this should be the same, right? Then one is decaying very fast. So here we have this kind of, there is some subtraction here, and this is this one. Okay, so time constant is determined by 1 divided by omega GC. Okay, this is the lower. This pole is located at lower frequency. This high frequency one is fast disappeared, right? And from this, so this is the tau. Then if you take a look at this starts from 0. Okay, there's no initial jump, so it goes like this and come back like this. Okay, and this is the estimation of settling time, which is 0.5 millisecond. Okay, so for this case, the response time of step input response and the step load response are the same. All of them are determined by compensation 0. Okay, if you go back to the voltage mode case, this step input was determined by low frequency, omega G1, so very slow, and the step load response is determined by omega G2, which comes later. So step load response was way faster than step load response. Okay, but this case they are the same, and both of them are controlled by one frequency, compensation 0. Okay, so okay, remaining part is about the loop gain. Okay, so loop gain comparison between voltage mode control and current mode control when converter changes its operational mode from CCM and DCM. Okay, let's take a look at this first. This is the loop gain of voltage mode control. So this is the conventional one. This is the regular one. Okay, this is and TMS prime is TBS. Okay, so this is the normal case. But if this load resistance increase, then converter goes into the DCM, then double pole split into two real poles, okay, and then midband gain is reduced like this, okay. So pole splitting occurred here, okay. It contains Dewey ratio to output transfer function, and in the CCM there is one double pole. But in DCM, double pole is split into two real poles, and the midband gain is reduced, and that impact is transferred to this directly. Okay, so this is the gain, loop gain for the CCM, loop gain for the DCM, and the crossover is reduced this much, and the midband gain is reduced this much, and this will degrade the output impedance and the step load response characteristic of this voltage mode control in DCM compared with the case of the CCM. So that was the one problem of voltage mode control. Let's take a look at the case for the current mode control. For current mode control, this expression is given like this: TBS divided by 1 plus TIS. And at this frequency, where magnitude of current loop is larger than unity, then you ignore this, and this is the ratio of this. Okay? And CCM case, there's a double pole. Okay? What DCM case, this double pole is split into two real poles, but same thing occurred here. That means ratio remains the same. Okay? Here you have only TBS, then that behavior splitting of double pole is directly influencing to this, but in here, so that splitting occurs here, they cancel. There is no effect. Okay, so this loop gain and this loop gain is almost the same. Not exactly the same, but almost the same. Though there is no huge difference between CCM and DCM, as is the case with voltage mode control, that kind of phenomena is not occurring here. Okay, they remain the same, right? Okay. If you intend to design current mode control, and you properly, successfully designed your controller, then you will see this kind of behavior. But somehow you reduce this omega Ci by increasing this SE. That becomes what? Voltage mode control. It goes to the direction of the voltage mode control, then everything becomes very similar to this. Okay, that is the voltage mode control, right? So if you follow the design rule, you absolutely have this kind of behavior, right? And output impedance characteristics is shown here. This is the voltage mode case, voltage mode control case. This is the CCM output impedance here. And if you move to the DCM, the output impedance is magnitude is increasing, which is a bad sign. And initially, the pole frequency is somewhere here, but there is some frequency, and it shows some peaking. So there is some oscillatory behavior in the transient response. Okay, we went through this before. Okay, and move to this side. Okay, this is the output impedance of converter with current mode control, but somehow I selected this omega Ci is 0.2 omega S. this is a very conservative design. I can go until 0.5, but somehow I selected this. Then this is the CCM case. This is the DCM case. There is some difference, but difference is very small. Okay? There is no huge difference here. There is a huge difference here, very small difference here. Okay? So they remain almost the same as the case of this loop gain. Okay? So loop gain remains about the same, and same is true for the output impedance. Okay? Why is that? That is also obvious too. Okay? So assume this is the GO prime. Prime is with voltage mode control. Then this is the output impedance expression. GPS is open loop load current to output transfer function, and TBS is here. And at DCM, there is a pole splitting is occurring here. The splitting, oh boy, not split. Splitting is occurring here. That affects this one, and this is reduced. Then this will be increased like this. And there is one omega G prime at lower frequency, omega PG prime. Originally, omega PG was here by design, but it jumped to here. Okay, and this one looks better. Only the reason for this is because we select this number. If you select 0.5, okay, if you select omega CI is 0.5 omega C, what you will have is output impedance will be very similar to that, something like this. Okay, so this one and this one will be similar. This is the CCM and the DCM case. DCM case will be larger, but they remain the same. Okay, this DCM. So these two are with CCM and the DCM. Understand this? Okay. This is not fair game. Okay. So this is optimized. This is increased to the extreme case. Okay. Maybe best possible design. And this is the very conservative design. If you increase this one to 0.5, pushing everything to the higher frequency, then you will obtain very similar to this. Okay. Why it remains almost same between CCM and the DCM is also shown here. Okay. So this is the output impedance characteristics in current mode control. We have TB 1 plus TI here. So this will be reduced. Pole splitting occurs here, so they are cancelled. Okay. So the change between CCM and DCM does not affect much here, but it has very dramatic change, which is the problem of voltage mode control is solved in current mode control. Okay. Finally, let me show the transient response of this. This is the transient response of voltage mode control. Okay. This is the step load response, very fast. And this one is very slow, oscillatory. Okay. This is the step. No. This is step load response. All of them are step load response. And this is the CCM, and this is the DCM. Because at the DCM, our magnitude of output impedance is increased, and it has very low pole, and this generates some oscillatory behavior. So that is reflected. So this is CCM, DCM. Okay. So very different. So CCM is excellent, but DCM is very poor. But here, this is with current mode control. This is the CCM, and this is the DCM. They are almost the same, very similar. Okay. If you increase, this is with this design. Initially, I selected omega CI is 0.2 omega S. This is omega CI is 0.2 omega S. Okay, 0.2 omega S. Okay, but if I select this, okay, I push everything to the extreme design within stability, then I will have this one, this CCM transient response and very similar transient response at DCM, which is very similar to this. Understand this? Okay. So current mode control is way better than voltage mode control. Okay. So this is the end of this design example. So through this design example, we reviewed all the design process. Okay. We found out there is one important number, only one important number in current loop design is slope of compensation lamp. In the voltage loop design, one important number is what? Loop gain crossover frequency omega CR. You will see that later. Okay? And we went through the closed loop performance. So closed loop performance provides many useful information about your system dynamics, and it provides some information to optimize your design.